Okay, so today we're going to talk about charge pump and voltage multiplier circuits. Okay? So we're going to start with a review of clippers and clampers that we talked about last time. We can go over some of the clipper and clamper homework if anybody has questions about that. Then we'll go on to our lecture. We'll talk a little bit about what voltage multipliers and charge pumps actually are. Basically, they are circuits that increase voltage. So they help you start off at a low voltage and you go up to high voltages. Voltage multipliers do that starting with an AC signal, going up to a high voltage DC, and then charge pumps are very similar, but they start with a low voltage DC and go up to high voltage DC. So that's the basics. We'll talk about why they're important, then we'll get into some details about voltage multipliers and charge pumps and how they actually work. Then we'll do a preview of today's lab. You guys get to make your own voltage multipliers and charge pumps. And then I just wanted to remind you about the homework. It's all posted on the syllabus page, so make sure you're checking in with that. There's some reading there to help you guys prepare for these classes. And there are also some online quizzes that you should be able to do now. There's a quiz about power supplies and a quiz about diodes and semiconductors that you should be able to work through. Okay? So any questions before we get started? Cool. So then let's start with a quick review of clipper and clamper circuits. So what was a clipper circuit? What was the general definition? Yeah, a circuit that limited a certain amount of voltage. So it would clip off any voltage that exceeded a certain level. And really, a clipper circuit is one that uses diodes. To limit the voltage. So that was a clipper circuit. So we talked about a couple of different examples of clipper circuits. The simplest one looked like this. So this was an AC signal. And so the incoming AC signal was a sine wave, or something like this. And then this diode would limit the amount of voltage that we could get on the output. So if we had a positive voltage up here and a negative voltage down there, this voltage would increase. We'd have a positive on that side of the diode, the anode, and a negative on the cathode. Is that diode forward biased or reverse biased?
Forward.
Forward. So what's the maximum voltage we can have across there? Yeah, about 0.7 volts, give or take. So when the incoming voltage went positive, the output voltage would go up, and then as soon as it got to 0.7, we get clipped off, right? That's why we call it a clipper circuit. But now let's see what happens when the incoming voltage is negative. So here we had a negative voltage and a positive voltage down there. So we had a negative and a positive. Was this diode forward biased or reverse biased?
Reverse.
Reversed, exactly. So since it was reverse biased,
Nothing.
it was as if it was not there. So when we're measuring the voltage across that diode, it can go up as high as we want. So it goes something like that. If we had a load resistor over here,
Split it if they're equal.
right, so some of the voltage would go across this resistor and some would go across that. And if they're equal, like you said, it would be split 50-50. If one is bigger than the other, one of them is going to get more voltage than the other. Yeah.
What's the formula for figure that out.
So the formula for a voltage divider, let's say that you have two resistors like this, and you've got an input voltage up here. This is R1 and this is R2. The basic idea is that if R1 has 50% of the resistance, then R1 gets 50% of the voltage, and so on. The exact formula for that is that VR1 equals V in times R1 over R1 plus R2.
Okay.
And VR2 equals V in times R2 over R1 plus R2.
And that works for several as long as they're in series.
Yeah. So if you had 3 resistors, it would be the voltage on R1 would be R1 over R1 plus R2 plus R3.
That's cool.
Yeah. Yeah.
So as long as you know, if you just have 2 resistors, if you know one of them, then you definitely find out, you know,
If you know
how much voltage is.
Yeah, if you know the voltage across one of them, and you know the total voltage, you can find out the other voltage.
Yeah.
If you want to use this formula, you have to know both resistance values.
Yeah.
Yeah.
Yeah. Okay. Sweet.
Yeah. All right. So that was the basic form of a Clipper circuit. There's lots of other forms that it can take, but I'm not going to go through every single one right now. But if we have some questions about the homework in a minute, maybe we can do 1 or 2 of those. Did you have questions about how this Clipper circuit was working? Okay. So then, the other type of circuit that we looked at was a clamper circuit. So a clamper circuit is a circuit that adds a DC bias or offset to bless you, an AC signal. So if you have an AC signal like this, it's a sine wave and it's centered around 0 volts, a Clipper circuit will take that and give you a signal that has the same shape, but now it's been shifted up. So now the middle part of that signal has been moved up. Yeah.
Now, is there a reason why you'd want to move an AC signal up like that?
Yes, actually. The clamper circuit is kind of the foundation for the voltage multiplier circuits that we're going to see today.
Oh, okay.
Yeah. So we use these types of circuits, and we actually chain several of them together in order to give us a voltage multiplier circuit.
Cool.
So we can, get much higher voltages. Yeah. So the simple form, So are there any questions about the clamper circuit? Okay, then does anybody have questions about the Clipper and clamper homework? I'm happy to do 1 or 2 problems if anybody has 1 or 2 that they are interested in.
Number 6.
Sure.
No, I wanted to do 5, but that's okay.
Well, we'll do 5 next.
Okay.
So what page these are on?
38.
38, okay, perfect. All right. So number 6. We've got a 12-volt AC signal here. Got a capacitor, and then a diode, and then the load resistor. So we need to sketch and label the output, it says. So let's look at what is happening in the case when we have a, let's start with the negative voltage up here and a positive voltage down there. We've got a negative voltage there and a positive voltage there. So is that diode forward biased or reverse biased?
Forward.
Forward, exactly. So how much voltage is across it?
0.7.
Yeah, 0.7 volts. So then we know that we have 12 volts total from here to here. We know that we have 0.7 across that diode. So how much is left across the capacitor?
9.0, no,
11.3.
11.3, that's right. Perfect. So that capacitor charges up to 11.3 volts in this case. Okay. So then, let's see what happens when this voltage goes positive up here and negative down there. So now, is this diode forward biased or reverse biased?
Reversed.
Reverse biased. So it's like it's not even there, right? It doesn't conduct any electricity. So then we have 11.3 volts up here plus, or I'm sorry, we have 12 volts up here plus the 11.3 from the capacitor. So that brings us up to 23.3 volts. So our incoming sine wave looks like this. It goes up to a maximum of 12 volts there. Our output sine wave goes like this. It's now centered it's got a center line that's right here at 11.3 volts.
Wouldn't it peak at 6 volts?
I don't think so, because this is 12 volts peak
Oh, yeah.
rather than peak to peak. Yeah. Right, if it had been 12 volts peak to peak, then it would be 6, yeah. So the new wave, the output wave, is centered here at 11.3, and it goes up to a maximum of 23.3, and then it dips down just below the
Would it dip down to 0.7?
Yes, exactly, to minus 0.7.
Yeah, minus 0.7.
Yeah. So the lowest point here, minus 0.7 volts, and then the highest point is 23.3 volts. So it's still the same shape. It's still 12 volts from the middle to the highest point, and 12 volts from the middle to the lowest point, but it's been shifted up by 11.3 volts. Okay? So questions about that?
So you use this kind of circuit when you want your peak voltage to be positive, peak to be.
Lift it up, yeah. Exactly. Okay, so that was number 6. So Margaret asked about number 5 also. So let's take a look at that one. So with this one, yeah, R1 isn't really labeled here, so that makes it hard. So
Yeah. Is it supposed to be, or are we supposed to do the
yeah,
math?
I think we're.
I have R1 on there.
Well, there's a label
There's
for
no
R1.
value.
Yeah.
Oh, like the value of it. Oh, yeah.
Right. So we're going to call that one 5
Interesting.
ohms also. All right. So let's see. So this is ohms. This is 3 kilo ohms. All right. So let's see what's going on here. So when we have a positive voltage up here and a negative voltage there, is this diode forward biased or reverse biased? Yeah, it's reversed. So it doesn't conduct, so it's like it's not even there. So
Split voltage.
yeah, exactly. And this is 12 volts
10.
peak. Oh, I'm sorry, 10 volts peak. Yeah. There. So, right, we split the voltage. So the incoming wave, like this. The outgoing wave gets split, the voltage gets split across there, so half goes on each of the resistors. So the maximum output is at 5 volts. So it goes like that. It's positive. And then when you have a negative voltage up here and a positive voltage down there, this is when it gets a little bit interesting. So is this diode forward or reverse biased though?
Forward.
Forward biased, that's right. So now we have to figure out what's going on with this one. So we know that we've got negative 8 volts there. And this one is has 5 kilo ohms and this one has 3 kilo ohms. So that means that we get 5 volts across this one and 3 volts across that one. We're starting from 0, we go down by 3, so this voltage right there is at minus 3 volts. Did I go too fast on that one? Should I do the math? Yeah, basically all of the voltage adds up to 8 volts and the resistances add up to 8 kilo ohms. We picked these numbers so that the math was easy, or relatively easy to see. In real life, the numbers would be, they could be anything. And the math wouldn't be as easy, so you would have to use the formulas to do it. But since it's 8 volts and 8 kilo ohms total, each kilo ohm gets 1 volt. So 5 kilo ohms gets 5 volts, 3 kilo ohms gets 3 volts. Okay. So we have minus 3 volts there. So what is the, so we're at minus 3 volts there, and then how much voltage do we have?
0.7, minus
Yeah.
0.7.
Exactly. So 0.7 volts with going negative in that direction. So the least voltage that you could have here, the minimum voltage would be 3 minus 0.7, or minus 3 minus 0.7. So minus 3.7 volts. Does that make sense? Not so much.
Okay, because that's the negative 3 volts and the 0.7.
Yeah.
Okay.
So you start at 0, you go down by 3, and you go down by another 0.7, so you end up at minus 3.7 when we get up there. So on the negative side, it gets clipped off at minus 3.7 volts. So it goes down, down, down like a sine wave, and then it gets cut off there. And then it comes back up. Like that. Okay. Questions about that? Okay, cool. So that was a little bit about the homework. So then let's go on to our lecture. Let's talk about voltage multipliers and charge pump circuits.
So when you do your calculations of that, you just say 8, you don't do negative 8.
So let me draw it. Let me draw a voltage divider with that again. So you've got this voltage here is minus 8 volts, and then I think we said this was 5 kilo ohms and 3 kilo ohms. So V in is this voltage up here. So VR1 is minus 8 volts times 5 kilo ohms over 5 kilo ohms plus 3 kilo ohms. So that is minus 8 times 5 over 8 minus 8 volts. So that is minus 5 volts. Yeah, the 8 and the 8 cancel out. So you're left with minus 5 volts. So what that's saying is that there is 5 volts across this resistor, and the top part is negative, and the bottom part of the resistor is more positive. So if you're going from this side to this side, from the top to the bottom, you would be increasing your voltage. If you went from the bottom to the top, it would be decreasing. Is that what you were asking?
One, well, what I was asking is, like, if when you're doing the calculations, when you have negative 8 volts, do you put 8 volts in your calculation? Do you put 8 in your calculation, or do you put negative 8?
In this calculation, or in which calculation?
Well, in any case where you have a negative voltage,
Right.
how would you work with that? With 8 or just with negative?
The important thing about voltage is you remember which direction is positive and which direction is negative. So, I would use the actual negative sign when you're doing the calculations, but when you're actually putting it on your drawing, it's important to label it, and the side that's more negative is the side towards the more negative voltage. The side that's more positive is the side that's closer to the more positive voltage.
And when you're using the negative voltage with the polarity, like capacitor and stuff, that's going to be reversed. The positive side of the cap.
Right. So if this was a negative 8 volts there, and we had a capacitor in parallel with this resistor, for instance, then the negative side of the capacitor would be like that towards the negative supply, and then the positive side would be towards ground. Yeah. Yep. Other questions? Okay, so let's talk a little bit about voltage multipliers and charge pumps. So like I mentioned earlier, the goal of these circuits is really to take a low voltage signal and increase the voltage. Voltage multipliers work with AC signals coming in. Charge pumps start off with a DC signal and boost it up, but they kind of cheat. Basically what they do is they start with the DC signal, and then they use a little an integrated circuit to create a square wave and essentially create their own AC signal, and then they boost that up. Okay, so in a way, they're kind of like a type of switch mode power supply, because they take a DC signal and they switch it on and off quickly, and then use that to boost up the output. Okay. So that's what they are. There's circuits that multiply and increase voltage. So why should we care? Can anybody think about a device that might need to take a low voltage and turn it into a higher voltage?
Amplifier.
Yeah, radios and amplifiers. Those take small signals and increase the signal and keep the same shape. So that's very important. In this case, we're talking about taking like just a power signal, a smaller power signal, and increasing the power, or increasing the voltage of that. So one example is a taser. Okay?
Oh.
Yeah. So
We're gonna make some tasers.
I absolutely cannot condone tasing anybody.
Dang it.
I know. But yeah, if you have a taser, you start off with you know, 4 AA batteries or something.
Yeah, they go
Each
like
one
millions
is-
of volts. Right?
Yeah, each AA is about, you know, 1.5 volts. So you start off with about 6 volts. And yeah, they go up to thousands, hundreds of thousands, very, very high voltages. Maybe millions, I don't know. Very, very high though. So
Ignition system for signifiers.
yeah, ignition systems. Camera flash equipment.
Oh, yeah.
Yeah, you have to have a very high voltage to trigger or to make that light go very, very bright.
Oh. Railguns.
Yeah, again, I can't condone any sort of weapons, but EEPROM chips are another example.
Oh,
The memory chips that go in computers actually need a high voltage in order to erase them and wipe them out so that you can write over them again. So that's another example. And then high voltage physics experiments also. When people are doing experiments with lightning and things like that, they want to recreate lightning in a closed, contained, regulated environment. They need to get very, very high voltages to do that. So that's another place where these types of circuits can be used. So we've already seen some devices that can increase voltage, right? Transformers will increase AC voltage, but there is a limit to how much they can increase it. Once you go too high, what happens is that the windings of the transformer, the insulation on the winding starts to break down. When you have very, very high voltages on those wires that are right next to each other, the insulation can start to break down. So the circuits that we see can actually have their components spread out far away from each other so that the physical space between them acts as additional insulation beyond whatever's on the wires. Okay. And then also transformers don't work with DC voltages. So if you need a high voltage DC, you need some other type of circuit like the ones we're going to see tonight. Okay, so that's why we care about these. Those are some examples of circuits that actually use voltage multipliers and charge pumps. So let's see what a voltage multiplier circuit actually looks like. Yeah.
So what would be the benefit of increasing the voltage of just a DC supply? Why not just convert it from AC to DC to high voltage, then to DC?
Well, so like I said, you could increase the AC voltage with a transformer, but so that can only go so high. So
Okay.
it could go to maybe thousands of volts. If you want to go beyond that, then you
Because
need
it's going to melt the coils.
right. It could melt the insulation. Exactly. All right, and even beyond melting, even if the insulation didn't melt, the insulation is only rated to a certain amount of voltage. So basically, voltage is the amount of force that's trying to push those electrons towards each other. So if you have too much voltage, it can jump through insulation even if it hasn't been, melted by heat.
The electrons pass right through.
Yeah, exactly. That's what happens when you walk over and you walk across a carpet and you touch a door handle and you get shocked.
Or someone else.
Yeah, or someone else, right. Air is an insulator, and normally it blocks electricity from flowing through it. But when you walk across a carpet, you end up with a very, very high charge on you, a very, very high voltage in the tens of thousands of volts.
Wow.
I mean, you wouldn't think so, but you can actually build up a whole lot of charge. And then when you get close enough to the door handle, the electricity is actually able to jump across that air gap and create the spark. That's why you can see that little spark sometimes. So it's able to jump through insulation. Yeah. Yeah. So let's talk about a couple of charge pump circuits. So we're going to look at a couple different kinds. We're going to look at the half-wave multiplier first. So A half-wave multiplier starts with a transformer. When we're building the circuit in class, we're going to use the transformer to step the voltage down, because we don't want to be working with the voltage coming straight out of the wall, because that's dangerous. But if you were trying to achieve a really high voltage, then, like Jason said, you could use the transformer to step up the voltage to begin with. So anyway, you have a transformer, and then we have a capacitor and a diode. And then another diode and another capacitor. No, I think this is the way that, it might not be the circuit that you have in the lab, but this is the way that I want to do the example for right now. So, so let's look at the case when we have a positive voltage up here and a negative voltage down here. So with these circuits, what happens is that it takes a couple of cycles for them to get charged up and fully functioning. So I'm just going to show I'm going to start by showing what happens in the first part of the circuit, and then we'll go on and show what happens in the second half of the circuit. Okay? So during the first cycle, we have a positive voltage here and a negative voltage there. So is that forward biased or reverse biased? Forward, right? So electricity flows through there. I'm going to say we have 10 volts peak coming in. And these circuits have a bunch of these diodes in them. And if I try to keep track of all of the diode drops, it kind of makes my brain hurt a little bit. And I think it's not as helpful to explain the general idea. So I'm going to neglect the diode drops here. You guys know that they actually happen, but I think it's clearer what's going on if we just leave those out for now. Okay? So this diode is forward biased. We have 10 volts peak. So this capacitor gets charged up to 10 volts, right? All right, so that's the first part. And this is it's more positive on that side and more negative on the right. Okay. So that's what happens during the first part. And then we end up with a negative voltage there and a positive voltage there. So now we can look at the second half of the circuit as well. So now we have a positive voltage there and a negative voltage there. Is that diode forward biased or reverse biased?
Reverse.
Reverse. So that one behaves like it's not even there. Over here we have a positive voltage and a negative voltage on that diode. Is that one forward biased or reverse?
Forward.
Forward. So electricity can flow through that one. So now we've got 10 volts there. We've got 0 volts there. This is plus 10. So we start at 0, we go down to minus 10. We go, so we have plus 10 less volts there. We have 0 volts there. So this capacitor gets charged up with 10 volts. that side is positive and that side is negative. Okay? So now the circuit is fully charged up, and we can see what happens when we end up with a positive voltage up here again and a negative voltage down there. So now we've got positive voltage there, negative voltage there. So now this is plus 10 volts there. This is 0 volts right there. This capacitor is still charged up. The electricity is flowing through this diode. So what happens is that you go 10 volts, you end up with 0 volts there. That diode is not, so that diode is not conducting. So at that point, you end up, let's see. Let's see. So you're at 0 volts. What's that? So you're at plus 10 volts there. You're down at minus 10. So this one is essentially, you have 0 volts there. And then you go okay. Well, you end up with double the voltage across that capacitor somehow, and I'm just not seeing it right now. So you start with 10 volts, you lose 10 volts across that capacitor, you end up with 0 volts there.
Do you, I have a question.
Yeah.
Does it go down to 0 volts or negative 10? Because it's AC.
Well,
Induced.
no, this side is at 0 volts.
Oh, when it's at 10, when's that positive, that side is 0. Okay. So
Right. Yeah.
it's
Right.
confusing.
So yeah, I know. Yeah. So you get plus 10, you get 10 volts across there, end up with 0 volts.
So you're supposed to get double the voltage across that capacitor?
Yeah, you end up with double the voltage across the output capacitor.
Oh, that's the output. Okay.
Does it go down to the positive forward bias? Yes.
So it goes down through.
Press the 0, it goes down and into the right.
To the right. So, well, you end up with 10 volts, and then you lose 10 volts across that capacitor. So you're at 0 volts there, and then you end up back at plus 10 volts there.
Because the capacitor is reversed.
Yeah, you go down by 10 volts there.
Isn't the capacitor charged at 10?
Oh, yeah.
At 10?
The direction matters, doesn't it?
Yeah, the direction matters. We start with 10 volts there. Then because of the direction that this one is charged, we lose 10 volts when we go across that.
Yeah.
Is that what you're? And then we end up with 0 volts there. And then over here, this one is already charged. So let's see. So when this one, so then everything stays charged. So then let's try it one more time down here. We end up with with plus 10 volts there and 0 volts over there.
Well, didn't,
Oh, okay, so that was what happened. All right, so when we have plus 10 volts here and we have 0 volts there, then we lose 10 volts across there. So this one is at minus 10 volts right there and plus 10 volts there. So then this capacitor gets charged up to 20 volts.
Oh.
Does that make sense?
I thought so.
Yeah.
Yeah.
Okay.
Sorry about that. So, okay, so let's go through this one more time. So when we have 0 volts up here, this capacitor is already charged up, and it's got 10 volts across it. So we start at 0, and then we lose 10 volts across that capacitor. We go down, so we end up with minus 10 volts right at that point there. With me so far?
So this is the
All right.
second cycle.
Yeah, this is right when we have a positive voltage down here. And then, so we have negative 10 volts there. We've got positive 10 volts there. So we have minus 10 volts on one side of the capacitor and plus 10 on the other side. So that's a difference of 20 across the capacitor, neglecting the diode. Okay?
Okay, that makes sense.
Let me see my picture real quick.
Yeah. So we have 10 volts peak coming in, and we end up with 20 volts across the capacitor.
Yes.
So the 20 volts is the peak,
So the 20 volts is a DC. So we have 10 volts peak AC coming in. So the incoming signal looks kind of like this. So this is 10 volts there.
Okay.
And then the output is at 20 volts DC.
Because of the output is a capacitor.
Right. The output is across the capacitor. And you would have a load resistor like over here. So if you were charging up a flash or something, then you'd be charging that load. Yeah.
So could you use this like as a power supply if you're converting AC to
Yeah. So if you
DC?
Yes, yeah, it would be you could use it as a DC power supply. You could, yeah. All right, so that's a half-wave multiplier. So questions about that? Because it
Two
only
diodes.
Yeah, it only charges during the. It basically only uses half of the signal. So so we'll see that the full wave multiplier looks similar, but it's got extra capacitors. So this is the half wave. The full wave, and it starts with the transformer. So this is the full wave multiplier. So basically it has the same sort of cyclical action as the half wave. So if we have V in here, the first capacitor gets charged up to a value of V in when the electricity is going around that way. Then the electricity goes around this path here, and this capacitor gets charged up with the full V in plus this V in up there. So this one ends up with 2 V in. And then this one also ends up getting charged up to 2 times V in. Okay? And you can see that this is sort of a chain. So we could just keep adding links in the chain and getting more and more output voltage, going higher and higher. Yeah?
And would all the rest of the capacitors be 2 V in?
Yeah, they would all be 2 V in after that. And we take the output from here to there. So in this case, V out equals V in plus 2 V in, so 3 times V in. Okay, and if we added another stage, we could be up to 5 times V in, and so on.
Oh, so you just keep adding
Yeah,
forever.
yeah, you could just keep going on. Eventually, you get to, you lose a little bit across each of these diodes. So you lose a little bit each time. So it's not perfect. You couldn't just keep going for, forever and ever, but you can keep going for a long time. Also, eventually, the voltage gets so high that it can start to jump from one component to another. So because of that, when people actually make a full wave multiplier, they often have it in a slightly different organization on a board or on a circuit. So they have a capacitor down here, and then they have the diode going like this. So they have the diode right there, and then they have another capacitor up there, and then another diode like that. So this actually puts physical space between all of your components to add extra insulation. And so when you're building the circuit tonight, I actually recommend doing it like this, just because it's actually easier to see in some ways, and it can help you keep track of what's going on a little bit more easily. So it physically spaces all of the components apart from each other, and it also makes it a little bit easier to see. Okay. So, questions about the full wave multiplier? Okay. So then, let's talk about a charge pump circuit for a minute.
This is one for the DC?
Yeah, the half wave and the full wave multipliers both started with an AC signal. The charge pump is going to start with a DC signal.
Yeah, this is one I need. Don't worry, you're not going to see me on the news.
All right, so basically it's like a full wave multiplier, but it starts with the DC signal. So we have a 5-volt DC signal there. And then this goes right across. And then we have our function generator here. Now, here we're using a function generator to create a square wave. But if you were building a circuit from scratch, you could just do this with a 555 timer. We used to make you guys use a 555 timer chip in this class, but that was just a little bit of extra complication that you didn't really need. So in the lab, you're going to use a function generator, but just know you could do it with a 555 timer as well. And we'll see those in a later class.
Sweet.
Yeah. So okay, so this is V out down there. We have our 5 volts there, and then the function generator is creating a square wave for us. Okay, so like I said, this function generator, or the 555 chip, is creating an artificial AC signal. So basically it's the same idea as before, but it's just creating an artificial AC signal from the DC. Okay? So what happens is that during the first cycle, the electricity flows around this way, and this capacitor gets charged up to 5 volts, plus and minus like that. Okay? On the second iteration, the electricity flows around here and back there. This goes up to 5 volts. You have 5 volts there, so this ends up with 10 volts, and you get 5 volts across this capacitor, plus and minus like that. And then on the third iteration, this is 0 volts there, and the electricity flows around like this. You end up with 10 volts there, and then the fourth time, this one gets charged up to 5 volts, like that. And you end up with 15 volts out at your output. Okay. So this is the way that it's laid out in the book. If you kind of squish things around and stretch it out, you could see that it was kind of like this. So get a capacitor up there. So this is your 5 volts there, and then down here, your function generator. So you can see it's just like your,
Oh, it looks like the other one.
yeah, it's like your full wave multiplier again. It's just been slightly rearranged, and you're using this artificial AC signal rather than the sine wave signal. Okay.
Oh.
So yeah, if you kind of stretch that end out and squish things around a little bit, it would look like that.
So I have a question.
Yeah.
So in this one, how do you know which way to put the capacitors? Like which direction to face it? On the one you just drew.
Right.
'Cause it-
So I think that in your lab book it should show which way they're actually supposed to go.
yeah, it's a little different drawing.
Yeah. So let's see.
In the lab book, it has actually a resistor and a couple of the capacitors.
Right. So, right, in the lab book there is a resistor right there, but that's not really going to affect the circuit.
Yeah.
There's a capacitor going between this 5-volt and ground,
Yeah.
but that's just acting to keep this 5 volts at a constant level.
Okay.
So that when the circuit demands a lot of electricity coming out of it, it doesn't dip down.
Oh, okay.
Okay. Also, the diodes in the lab book have these little extra curls on there.
The Schottky.
That's right. They're called Schottky diodes. And what a Schottky diode is it just behaves like a regular diode, but it's able to switch from its conducting state to non-conducting more quickly than a regular diode. So it's a little bit more efficient in this type of circuit.
Hmm.
We don't have Schottky diodes here, so we're just going to use the regular diodes. So it's not going to be quite as efficient. If you were really designing it and building a real one to supply power, you would want to be as efficient as possible and use the Schottkeys, but for demonstration purposes, the normal ones do work. Yeah.
So is this the same as the other one where you can just keep adding on to
Yeah.
make however much voltage you would like?
Right, exactly. Yeah, so you can keep going on and adding more and more stages to get higher and higher voltages. The higher voltage you go, the less efficient it is. So there's always a trade-off there. But yeah.
So one more question. For the lower drawing right here, are the capacitors the negatives facing to the left?
Yeah, so they would be facing towards the function generator. So that one would be like that. Let's see, up here. So it would be facing away from the anode toward the. Yep. Yep. So it would be like that, and then down there. So that one would be like that also, and that one would be like that. Yeah.
Okay.
Yep.
Ah, that looks pretty simple. I mean, that one looks way easier than
Right. Yeah.
to understand anyway. So
Yeah. I think it's easier to understand the, but yeah, it's up to you. So anyway, so that is a little bit about charge pumps and voltage multipliers. You're going to build those in the lab. A quick preview of the lab. When you're building the voltage multiplier circuits, be sure to use the center tap of the transformer. That way, you start off with a lower voltage. Okay, these are circuits that are amplifying the voltage. We want to start off with a low one so that it doesn't get to a dangerous level. Okay? So the TTL output on the function generator is on the back or the left. For this circuit, we're creating a square wave that goes between 0 and 5 volts. Another name for that is a TTL signal. So we use the TTL output on the function generator. So that's either on the left side of the of the function generator, or it's on the back of some of them. Okay. We already talked about the Schottky diodes, and then I would recommend wearing safety glasses for this lab because we are using the electrolytic capacitors again. It's easy to get them reversed. Try and put them in the right way, but do be careful. Okay. All right, and we already talked about the homework. So yeah, Jorel, do you have a question?
Yes. Part one.
Yeah.
The ground is on the middle part of the function generator. You use on the middle one?
Yeah, that's the center tap.
Or you set it up like that?
Yeah. Yeah. Other questions? All right, then you can take a break and do the lab.